Bismillahirrahmanirrahim. Assalamu alaikum, dear student. My name is Dr. Muhammad Adnan Asgar, and we will learn how to build multiplication table of different molecules under the subject of symmetry and magnetochemistry. Students, we have discussed and built some of the multiplication table of different types of molecules, which includes the most renowned one, water molecule, and ammonia. Moreover, we have discussed the multiplication table of trans 2 butene and trans 1 2 dichloroethylene. Now I would like to give a different type of example to build the multiplication table. For example, triphenylphosphine. This is a molecule named triphenylphosphine. So first of all, for making setup for the multiplication table, we should have to find out the complete set of symmetry elements and operations in triphenylphosphine. So first of all, we have to find out the symmetry operations. For finding symmetry operations, we must have to write identity, which is E, first for every kind of molecule. So let's start. So if I would like to write the identity E for the first symmetry element of the triphenylphosphine, then what would be the second one? We should go for the proper rotation. Yes, you need to find, is there any kind of proper rotation exist in this triphenylphosphine molecule? You better to think first. You should have to stop the video, and you should have to draw the molecule triphenylphosphine on a paper, and you better to find the symmetry operations. Yes, it's a time, it's your turn. Yes, after finding the your symmetry operations, you should have to compare your symmetry operations with the designed and with the actual symmetry operations and elements found in triphenylphosphine. The first one is the identity E. The second one, we should go for the proper rotation. For proper rotation, generally we can see there is a presence of C3. C3 means that molecule may come over there after 120 degree rotation, 120 degrees. So we can say there would be a C3 axis of rotation in triphenylphosphine. Yes, there is an other C3 which is actually C3 twice. If we repeat C3 two times, then the structure would be more indistinguishable as compared to the reference one. So far there are three symmetry operations and elements found in triphenylphosphine. The first one is identity, and the second one is C3, and the third one is C3 twice. So let's talk about the other symmetry operations and elements in triphenylphosphine. There is no improper rotation. We know that improper rotation was actually the rotation then reflection. So there is no S3 in this molecule. So there are two more symmetry elements which can be or cannot be found in this triphenylphosphine: the inversion center and the plane of symmetry, sigma. So let us talk about the sigma first. Is there any kind of sigma is present in this molecule? You better to find by yourself. First of all, I would like to give more information on triphenylphosphine. If you look at the structure of triphenylphosphine, you can clearly see there are two types of molecule. There are two types of atoms in benzene ring. The 1, 2 and 3 would like towards the observer, while the rest of the 3 is actually below the plane, actually towards or away from the observer. So if you critically watch this type of molecule in three-dimensional way, you can find that there is no sigma or plane of symmetry is present in this triphenylphosphine molecule. So is there any kind of inversion center? No, because we know that the inversion center was actually uh, that particular point in the middle of the molecule from where we can travel to anywhere. For example, I would like to travel in this side, and I found here a carbon atom, but oppositely on the other side there would be also a carbon atom. But in the case of triphenyl phosphate, there is no such type of property is found, so we can say there is no inversion center in triphenyl phosphine. So let's talk about the complete set of symmetry operations that is found in triphenylphosphine. The first one was the identity, and the second one was the C3, and the third one was the C3 twice. While there was no inversion center, and there was no improper rotation, and there was nothing about the plane of symmetry in triphenylphosphine. How we can say there is no improper rotation and the plane of symmetry and improper rotation? We have to better to further investigate the structure, correct structure of triphenylphosphine, and we should have to observe the structure in three-dimensional way for the betterment of for the better construction of multiplication table for triphenylphosphine. That was actually the old structure I have shown, and this is actually the structure of triphenylphosphine. Here you can see that these three benzene ring, the phenyl rings, are not actually planar, are not actually on one plane. So like in BCl3, we have studied the structure of BCl3 boron trichloride. We have already observed that BCl3 molecule was planar, and all the chlorine atom was on the same plane. So we can write so many type of sigmas and SN rotations, CN rotations, as well as multiple type of proper rotations we also studied in BCl3. But in this molecule, all the three adjacent molecules which is similar to each other, but they are not in one plane, they are not planar. So here you can see that you would not be able to find any kind of plane of symmetry or sigma in triphenylphosphine. So here is actually the complete set of symmetry operations and elements in triphenylphosphine. For the better understanding of the structure about the triphenylphosphine, and subsequently to find out the complete set of symmetry operations and elements in triphenylphosphine, we should better to go for three-dimensional structure of triphenylphosphine. Here we should go to Google first, and symmetry of elements of triphenyl phosphine. We better to write the symmetry elements of triphenylphosphine in Google. If you write the symmetry elements of triphenylphosphine, you would definitely get the structure at chemtube3d.com, and it's very comprehensive website to learn about the three-dimensional structures of many molecules. Here you can see that this is actually C3 rotation in this molecule, triphenylphosphine axis of rotation, and this is also the axis of rotation for C3 twice, which is discussed already. I have told you there is three symmetry operations named as identity C3 and C3 twice. So the axis of rotation for both C3 and C3 twice is same. If you rotate this molecule, that for example this phenyl would definitely come over there and the C3 rotation will complete. What happened if we rotate C3 twice, C3 two times? This definitely phenyl will join the place of this phenyl, and there is also an indistinguishable shape from the parent molecule triphenylphosphine. So the axis of rotation for C3 and C3 twice is similar. Here is actually the structure of triphenylphosphine. Here we can see this. This is actually uh, the molecule, which is, there is no kind of sigma is present in this molecule. We are unable to find any kind of plane of symmetry in this molecule, and obviously if there is no plane of symmetry, then the improper rotation would also not be counted, because improper rotation is actually the rotation then reflection. So there is no reflection in this molecule, so improper rotation is ruled out. There is also non-existence of inversion center in triphenylphosphine, because for example this is actually the middle point of the molecule, this phosphorus, and if we go like to this direction, if I would like to travel from middle of the point of this molecule to right side of the molecule, I will definitely find a carbon 7 of one of the phenyl group. So in inversion center it is mandatory that there would be a similar type of atom on the different side from just the middle of the point of that particular molecule. So there is no such type of carbon atom is present on the opposite side, so we can say there is no inversion center in this molecule. This is all about the structural description of triphenylphosphine, and here I would like to draw the multiplication table for the triphenylphosphine. Actually, before making multiplication table or construction of multiplication table for triphenylphosphine, we have better to at least draw the symmetry operation products. That, for example, what will happen if we applied identity to the molecule, and what will happen if we applied C3 to the triphenylphosphine, and subsequently what will be the result, what would be the result after applying C3 twice to the triphenylphosphine. We better to write on a paper the products of the symmetry operations that would be occurred in triphenylphosphine for the better construction of multiplication table for this particular molecule. Actually, here is actually the operation product of triphenylphosphine. For example, we have the triphenylphosphine molecule, and we just placed a upsided arrow on one of the carbon atom of phenyl group. This is actually for our reference only, so that uh, we can easily understand what would going to be happen if we applied symmetry elements and operation to this reference molecule. For examples, first of all, C3 identity means the first operation is actually identity, and identity mean is actually doing nothing to the molecule. So if we talk about the identity, the result would be the same, so no need to write the operation identity for this triphenylphosphine molecule. Let's talk about the C3. If we applied C3 to this molecule, the structure of the triphenylphosphine would be like this one. The arrow will definitely be upward, but on the different phenyl ring, because this phenyl ring will occupy the position of the second one, and definitely the result of the arrow would be like this one. And what will happen if we applied C3 twice, C3 two times? For example, we have applied C3 one time and we will get the result like this. So what will happen if we apply again C3 to this product? The result would be like this one, this arrow on the upper side. So we can say this is actually, we can directly perform C3 twice, and we will get the result like this. So on the basis of this interpretation of symmetry operations and subsequently the products of the symmetry operations, we are now able to construct the correct multiplication table for triphenylphosphine. So let's talk about the construction of the triphenylphosphine multiplication table. PPH3 is actually the sign for triphenylphosphine, and here is the symmetry elements: identity, C3 and C3 twice. Moreover, we should have to write the similar symmetry elements and operation on the in a column form, EC3C3 twice. Now we are able to multiply the one of the symmetry elements in the column with all the symmetry elements and operation in the row. We have to repeat this for all the symmetry operations that is written in the column with all the symmetry elements and operation which is written on the tabular form in the row. So first we need to multiply identity with identity. The result would be again identity, because identity is actually doing nothing. What will happen if identity multiply with the C3? The result would be C3, because if we applied identity to the molecule, then there is nothing change in this molecule. So after applying identity, we need to perform C3 operation to the triphenylphosphine. The result would be same, which is C3. If identity is multiplied with the C3 twice, then the result would be C3 twice, and this is actually the reply of the first multiplication element multiplication table of first element, which is identity, with the rest of the symmetry elements and operations. So from here C3 we should have to multiply, we should have to apply the C3 to triphenylphosphine and then identity. What will happen? This is actually C3, because after applying C3 to the molecule, the result would be C3, but after applying C3, then there we need to apply identity, which is doing nothing. So the result is C3 over here. Again, if we talk about the C3 multiply with C3, what will happen? If we apply C3 and then C3 again, then it would equal to C3 twice, because C3 two times mean the operation the sample would yield the result like this one. So if we apply C3 two times, then it would be equal to C3 twice, and it is better to write here add C3 and C3 twice over there. What will happen if we apply C3 molecule to the molecule and then C3 twice or C3 two times? It means we are applying C3 three times, one time C3 and two times C3 twice. So what will happen? It is actually C3 three times. So if we apply C3 three times, for example, I am applying C3 one time, the molecule, the arrow is over here, and if I applied C3 two times, then the arrow would be on this position. And what will happen if I again apply C3 to this molecule? This arrow would definitely join the same place, which is the starting place. So C3 multiplied with C3 twice is equal to identity. So we can say this is actually the complete set of symmetry operations of C3 operation with the rest of the symmetry elements of this molecule. Now let's talk about the third symmetry operation, which is C3 twice. Now we have to multiply C3 twice with all the symmetry elements and operation of triphenylphosphine. So first of all, C3 twice, if we need to apply C3 twice to the triphenylphosphine, then we better to multiply with that result with identity. The result would be C3 twice, because identity is actually doing nothing at all with molecule. So here we need to write is actually C3 twice in this position, in the first position. So second operation is actually the C3 twice with triphenylphosphine, then C3. So what will happen? We need to apply C3 twice first, which is actually, if we applied the C3 twice, this arrow will definitely come over there. And what happened if we apply C3 again after applying C3 twice? This arrow will definitely join the place over here, and if this arrow will take the position over there, it means this is equal to identity, which is actually the starting point and the starting position of triphenylphosphine. So we can write that the product of this operation C3 twice and C3 is actually identity E. The third one is C3 twice with C3 twice. What will happen if we applied C3 four times? We need to apply C3 twice, two times, C3 two times, and then again C3 two times. What will happen if we applied C3 four times? What will happen? Yes, we can multiply C3 four times to this molecule. What will happen? Here we are going to apply C3, and the arrow from this position will definitely over there. This actually molecule rotate and get the position over there. So this is first C3. Now talk about the second C3. If we apply 120 rotation again, 120 axis, then this molecule, then this portion of this molecule will actually replace over there and join this arrow will definitely join the place here. In this picture we can see that this is actually C3 two times. So what will happen if we apply C3 third time? We better to apply C3 three times. So what happened if we applied C3 three times? We better to apply C3 again. This one of the phenyl will definitely replace this phenyl group, and this arrow will join place here. So this would be equal to identity. So far we have uh, performed C3 three times, but we have to perform C3 four times. So after applying C3 four times, because we are performing C3 twice with C3 twice, so C3 thrice we will get the again identity. What will happen if we apply another C3 to this identity? The result would be like this one, and which is equal to C3. So we can write here C3, here we need to write C3 twice, because when C3 twice multiplied with identity, the result would be C3 twice, and the result would be the E identity when we applied C3 twice with C3. Identity was over there, and the result of C3 was obtained when we applied C3 twice with C3 twice. So this is the complete set of multiplication table for the molecule triphenylphosphine, and I do believe that you people got the point, and thank you very much for all.